Hi, everyone. This is spring of 2020, but the timeline doesn't really matter. Trigonometry, which is what this class is, hasn't really changed in quite a long time. What I'm going to show you today are actually some of the modern tools we use to do this, as well as how to do this stuff by hand. What we're looking at right now, this is 8.7 in our book, and 8.7 is on graphing polar equations and the polar coordinate system. So in the past, what we've done, we had something like X and Y, and this made a grid. And going to a specific point on the grid, like this is 1, 2, 3, 4. This is X equals 4. This spot right here is Y equals 3. This coordinate here was XY, which was 4, 3. How does that differ from polar system? Polar system, this was the XY system. Now we're looking at R theta. The graph changes quite a bit. Let me show you what it looks like on DESMOS and how to get to it. So, and I'll put the instructions in a second. In fact, let me write the instructions before I do it while I'm doing it, and then I'll draw the picture. How about that? I'll come back to the picture in a second. So, bringing up the polar graph in DESMOS. We like DESMOS because it's free to use. What you do is you come over here, and here's our DESMOS picture, our website. I've already logged in. I actually have a bunch of equations saved, but I have it in the regular rectangular or Cartesian coordinate system. All you got to do is come click on the wrench, and it says graph settings right here. And if we click on it, see where it says grid? I can switch over here, and it looks like a target system or a bullseye. I can tell it I either want radians or degrees. Okay. Let's go with degrees. No, let's do radians. Okay. And I'll close that. And this gives me a polar graph. So a polar graph has a bunch of concentric rings. And so, well, I was going to say what I did. In DESMOS, click on the wrench in the upper right. It says graph settings there. And then switch from, does it actually have words? It's in the grid section. It doesn't show it, or it doesn't say the names of it. Switch from the block grid to the circular grid or polar in the grid settings. And as a reminder, on the bottom, we can opt for radians or degrees. So I'll let you pause that for a second. So it's this wrench right here, and that's what we did. If you take the axis numbers off, it doesn't show them to you. I think it's handy to have some of them on. It's good to see what scaling they're doing. So let's go back to the graph I was doing. And it's got a bunch of concentric rings. So let me see if I can do this any justice. Not really. And now r theta, what this tells us to do, so let's look at a point like 260. So I'm going to look at the point 2 and 60 in radians is what? Pi over 3. So you might find it handy to have the 30 and 60 degree lines marked. And once you do one side, they translate over well to the other just by following the line through. Looks like Spider-Man's web, right? Looks like a spider web. So this is my r theta. And r is how far we are going from the center. So I'm going to go out from the center. I'm going to go out one line. I'm going to go out to 2 lines. So this is r equals 2. And then I'm going to rotate 60 degrees, or pi over 3. That's the point 2 comma pi over 3. Okay, so I'll write that in words. When graphing, move r units out from the center along the positive x-axis. And then rotate counterclockwise theta units, whether it's radians or degrees. Okay, so they usually call that thing the polar ray. Let me draw my circle again. And I'll just stop there. The positive x-axis is called the polar axis. Okay, and we just swept out 2 and then pi over 3. Maybe this time, what's that, a third one? Third ring, go out to 3. And I'll draw my angle marks in there, my 30 and 60 degree angles. I'm literally just breaking up each quadrant into thirds. And I'm eyeballing it. It's pretty reasonable. So I'm going to pick a point on the circle and let's discuss how we can get to it. This point right there. That's P. Now in the rectangular coordinate system, this has got a very, very fixed value. The polar coordinate system, what we have here is I'm going to have a line going from the center to it, and this is called the polar ray. Okay. How can I describe P in polar systems, polar coordinates? Well, the first thing I do is go, how many rings did I sweep outwards? I went out 1, 2, 3 rings and rotate around. I am on R equals 3. And then how many units did I swing outwards? I went 30, 60, 90, 120, 150 degrees. So that was me going like this and then following it that way. I didn't have to do that though. Okay. I have other options. I could have rotated, gone out 3, and rotated a negative angle. So this would be option B. This was option A. I still am going out 3 from the center, but now I'm going backwards 180 degrees and another 30. Theta could be negative 210. And yet there's more. There's even more ways to do this. So far, I've looked at theta being positive or negative, but R is actually a distance from the center along the axis to the right. So what happens if I sweep 330 degrees that would put me, let me do it on an inner circle. Actually, let me do it down here. I could go 330 degrees. Oh, I need my lines in. It's really hard to sketch this by hand if you don't have the 30, 60, 90 marks in there. 45s are kind of easier to spot. I can sweep around 330 degrees and then go negative 3. So the way I do this when I'm doing this is the easiest way for me to visualize. When you're using negative R, sweep out the angle first. And then go R the opposite direction. that's one way of visualizing it. Let me show you the other option of this. I'm going to show another way of visualizing this negative 330 in a second. I could have also rotated negative 30 degrees and then did negative 3. So this is the way I do it in my head. There's another way to do it. The only reason I'll show it to you, you might like it better. The only reason I don't do it is because I'm so used to 0 degrees being along the x-axis that changing that coordinate system just blows my brain up, and I can't effing handle it. I can't. Here's your other option for getting that negative radius. So we'll just do it right here. I'm going right there. Here, I'm going to go out -2 first. So r equals -2 first. And then second, I address theta. From here, I have to either rotate 180, 90 more is 270, 45 is 315. Or I have to rotate -45 degrees or positive 315 degrees. So those are my options. You'll see these interpretations work the way I did it. So here I moved R left first and then rotated. But if we match that up with the way I just described it, go out the 315 degrees first, would be going all the way around until you're right here, and then going the other direction 2 units. Or going -45 degrees and then going -2 units. So they both renditions get you to the same spot. Having where theta equals 0 degrees and 45 degrees really bothers me if it starts changing. I always want 0 right here. I want pi/6 right here. I want pi/3 right here, for example. Okay? So there are at least 4 ways to list a single point in polar coordinates without making multiple loops. I could very well add 360 degrees to that. And this is r equals -2, theta equals 675 degrees. It just starts getting clunky then, and it doesn't get very helpful. Okay? So how you write it or how it's written will tell you what they're looking for. So let me give you an example and ask you to find 3 other ways to write it. So your turn. Graph. I don't want to make the back graph too big. Let's go with 3 comma, negative 110, and list this point in 3 other ways. So pause it and take a second to take a look at it. Okay. You kind of want to make the lines when you're doing this by hand along like the X and Y axis, they're all equally spaced. And if you can do that and keep it looking like equally spaced going around the circle, you're not doing too bad. So one option, the one that it was asked for, was go out 3 units and then go negative 110 degrees. This would get me to negative 90. Getting all the way to this line would be negative 120. So we're looking at P being right about there. So we could say 3, negative 110 degrees. That was the one that we started with. At this point, I would do the one that just goes the other direction around the circle. So let's go the positive direction around the circle. We got to go 90 degrees, 180 degrees, and then we start adding increments. This is 30, 210, another 30 is 240, and this was 10 units away. This should be 250 degrees. And if you like looking at degrees in that might actually help you if you have DESMOS open, you're looking at it, pinpointing like, oh, here's 240, here's 270, 250 is right about there. And what other options do I have? I could go to the opposite side of the circle and use the opposite radius. So what is this point on the other side? This distance here was 20 degrees, which means that distance there has to be 20 degrees. That's how we keep that symmetry going. And I know this whole thing is 90, so I could go out 70 degrees. And then I could use a negative radius and flip to the other side. Or likewise, go -3 this way and rotate 70 degrees. And the other option is going counterclockwise around there. I've got 0, 90, 180, 270. Another 20 degrees is -290 degrees. And then we'll reflect using the negative radius. Notice let's see if I can put a coordinate in here. I don't know how to make degree. Ooh, maybe right there. It's got to be in there. This must be a way to do degrees. That didn't help. Ooh. Let's do pi. Pi over 3. Ooh, I got an extra letter in there. So hide that. Let's get this shrink back down. Turn off that black circle. So that should be going out 3 and then going pi over 3. I'm not sure why it isn't. Oh, yeah, I am. R equals 3. It's treating this as x and y. That's unfortunate. Maybe there's not a way to put it in polar. I'll have to look at that later. We will use these, have fun with some of these equations a little bit. It's actually a good thing to point out. Let me bring that back up. XY equaling 3 pi over 3 is not the same thing as r theta. When r equals 3, it's going to stay on that third ring. But right now, it's putting 3 pi over 3 right about there. Why? Well, what are our equations for polar? We have x equals r cosine theta, y equals r sine theta. Because notice it's not even on the pi over 3, or pi over 3 would be up here. It's not even on that one. So why is it down here? This is saying, okay, x is 3. What is r in cosine theta? Y is pi over 3. What's r sine in theta? So we would have to find r doing x squared plus y squared. And we would have to find theta doing tangent y over x. Okay. And notice these get you different values than what we see, because this is showing us in x and y. What does label do? I'd say, just put it. What's wrench do? It just helps describe where to put the label. Okay. So rather than using 3 and pi over 3, let's actually use a different point. Let's take a look at the point 6, negative 6 root 3. And this is in x and y. Find at least one way of writing this as polar coordinates. And we just discussed how to do it. R is the square root of 6 squared plus negative 6 root 3 squared. Theta equals tangent inverse of negative 6 root 3 over 6. This is square root of 36 plus 36 times 3. Which equals 36 times 1 plus 3. This is my way of doing it without the calculator. R equals the square root of 36 times the square root of 4. 6 times 2, R equals 12. Theta here is tangent inverse of negative root 3. What's the reference angle there? Root 3 comes from 60 degrees. We just got to figure out where this is. 6, negative 6 root 3 should be quadrant 4. Which means this angle here is 60 degrees. Or really actually negative 60 degrees. I can jump straight to it right there, right? I can write P as R equals 12, theta equals negative 60. Or if I wanted to go away the other way around the circle, R equals 12, theta equals 300. So on R equals 12, look at that. R equals 12, and it's backward 60 degrees. Okay. So let's look at some other things we can do. We can convert equations from rectangular to polar. So let's convert from rectangular to polar equations. Rectangular or Cartesian is another word for them. Equations to polar. And what are we going to do to use it? Our good old conversion formulas. X equals R sine theta, Y equals R, X equals R cosine theta, Y equals R sine theta, or we can do R equals the square root of X squared plus Y squared, or theta equals tangent inverse of Y over X. So in regular Cartesian, it's called Cartesian, named after Descartes, big grapher and cartographer, which is where they came up with calling cartography, was big on mapping things. And so Descartes, his system, the Cartesian system, a standard line is AX plus BY equals C. What happens in polar? We replace X and Y with their polar values. Usually they solve for R. So here I can factor out an r. And that leaves a cosine theta plus b sine theta equals c. And finally, we divide by that. And in polar system, r equals the constant over a cosine theta plus b sine theta. This is a straight line. Do I have that in Desmos already? I do. See that? So in Desmos, I did c equals 3, a equals -1, b equals 1. This would give me negative x plus y equals 3 from this line right here. And solving for y, this would give me y equals x plus 3. Is that what I have when I switch to Cartesian? I do. My y-intercept is 0, 3, and it has a slope of 1. So some things, like straight lines in polar, are miserable. Okay, so that's our first lesson. Not everything should be switched to polar. Y equals x plus 3, easy to graph. R equals 3 over negative cosine theta plus sine theta, same line, but atrocious. And I haven't shown you the atrocious part, graphing these by hand. Other things look great. What's the equation of a circle? Like, let's look at a circle of radius 3. We normally have x squared plus y squared equals r squared. X squared plus y squared equals 9. This is really only easy to graph in Cartesian because we learned how. But r is the square root of x squared plus y squared. This is where the circle thing really comes from. R squared equals x squared plus y squared. I get r squared equals 9, or r equals plus or minus 3. What else is being graphed? Not sure. R equals 3. I said plus or minus 3. Does it affect it? I made it negative. No, it doesn't. Because here, theta is unrestricted, the full circle. So we sweep out the full circle. I'm not looking at that. We sweep out the full circle. I don't know how long I had that down. Let me pause for a second. So we were looking at x squared plus y squared equals r squared, or in our case, the circle radius 3 is 9. This is easy to graph because we've learned how to graph it in algebra, college algebra. Let's switch to trigonometric form, polar form. R equals the square root of x squared plus y squared. We square it, we substitute it in. R squared equals 9, R equals plus or minus 3. And as I was showing in DESMOS, it doesn't matter which direction I go. I can either go out 3 and go this way, or I can go out -3 and go that way, and it's still the same circle. Great. Let's take a look at graphing something a little more challenging. Graph R equals 1 minus sine theta. We're going to do this without DESMOS. Okay. Pro tip, make a table. And you want to make a big table. 0, 30, maybe do 45, 60, 90. Don't stop. 120, 150. Maybe you only do every 30 degrees now. What is sine theta at these points? So I'm gonna, like, maybe every 2, I'll put a line in. That way it's easier to read my graph in a second. Easier to read my table. Sine of 0 is 0. Sine of 30 degrees is 1/2. Sine of 45 is root 2 over 2. What is root 2 over 2 though? Because I don't really know where root 2 over 2 is. So I'm going to put 0.707. Sine of 60 is root 3 over 2. Sine of 60, 0.866. Once you have 30, 45, 60 in there, we know reference angles are going to give us all the rest. Sine of 90 is 1. And now this starts ticking back downwards. We got 0.866. 150 is like 30, it's 0.5. 0. 210 is like 30, but now we're in the negative range. Negative 0.5, negative 0.866, negative 1, negative 0.866, negative 0.5, and 0. If you have all the 45-degree marks in there, let me make a note of this. If you have all 30, 60, 90, table is symmetric, or table is reflective, is reflecting. This 0.707 is throwing it off. Otherwise, I had 0, 0.5, 0.86, 1, 0.86, 0.50. If you put in 145, you might want to put them all in. You might want to have all in to keep your table balanced. Okay, now we wanted r equals 1 minus sine theta. So I'm going to do 1 minus this value. Here I get r equals 1. Here I get r equals 1 minus a half is 0.5. 1 minus 0.707 is 0.293. 1 minus that is 0.134, I think. 1 minus 1 is 0. And now it starts to ricochet. I can just follow it backwards, skip the 45 one since I didn't put it in everywhere. And now I'm going to do 1 minus negative 0.5 is really 1 plus it. 1 minus negative 0.866 is really 1.866. 1 minus negative 1 is 2. And then it starts to reflect going the other way. And finally, I'm going to draw my graph. I'm going to look to see what my biggest R is. R is biggest at 2. I don't need more than 2 rings. Does that make sense? So R caps at 2. Only need 2 rings. I'm going to put my 30 and 60 degree lines in there. Okay, now literally I have, this is theta, this is R. If I rewrite them as points, I could do this over here on the right. This is 1, 0, 0.5, 30 degrees, 0.134, 60 degrees, and I can do them all that way. The other way, looking at the table, is go, how many angles am I rotating? And then how far out do I go? When I don't rotate it at all, I go out to R equals 1, which is right there. When I go to my 30 degree mark, I'm only going out to R equals 0.5. My 45 degree mark's a little bit tighter. 60 is way down close. And when R equals 90 degrees, or theta equals 90 degrees, I go out 0. Now I go to 120 degrees. So I sweep out to here and I go out 0.134. I go to 150 degrees and I go out to 0.5. 180 degrees, I'm out to 1. So right now, this has done this. It looks like two little hills. At 210 degrees, this line right here, I got to go out to 1.5. At 240, I'm almost all the way out to 2. And at 270, I am at 2. And then it starts to shrink back in. And we connect the dots. It looks like a heart. It's called a cardioid. See? It makes a heart. It's called a cardioid. Let's do one more. And then we'll tinker with DESMOS and see what it shows us. I'm going to pause this though and have you do it. Actually, so let's look at this in its other form. Can I write this in terms of a X and Y? I could try writing this in terms of X and Y. R equals 1 minus sine theta. R is the square root of X squared plus Y squared. 1's fine. Sine theta is Y over R. So I've got X squared plus Y squared, the square root, equals 1 minus Y over the square root of X squared plus Y squared. If I multiplied both sides by it, I would get X squared plus Y squared equals the square root of X squared plus Y squared minus Y. And do you want to graph this? Thought the theta and R table was bad, didn't you? That one's an atrocious thing to do. We don't want to do it. So let me give you guys one to graph. Do not make assumptions that you know what's going to happen. When you do, you end up getting the graph wrong. It happens all the time. 4 cosine of 3 theta. And if you stop and reason about it, if you try to do 30, 0, 30, 60, 90, as soon as you plug this in, this is 0, 90, 180, 270, and you're skipping all the angles. You really want to go, so if we try to do theta equals that, 3 theta is this. maybe try theta equals every 10 degrees. That way, when we multiply by 3, we get the values that we know. Okay. So I'll start building a table while you're building a table. Hopefully you pause. So I only went up to 180 degrees. I'll see how that goes. That might be enough. I'm not going to stop at 90, even though going up to 120 gets me to 360. I really want to see what happens if I at least do half the circle. So if I do 4 times that, I've got the coordinate 4, 0. 2 times root 3. 3.46. It's about 3.5. 3.46, 3.5. That's at the 10 degree mark. 4 times that is 2, and that's at 20 degrees. 0 at 30 degrees. -2 at 40 degrees. negative 3.5 at 50 degrees. It starts following a pattern. And now it goes positive. Okay. So this is only up through 0 is less than or equal to theta, less than or equal to 180 degrees. I will graph this and see if I get enough. Maybe I should do one more just to see if it starts. Now, we'll do that afterwards. So I'm going to do this on another piece of paper where I can make this graph bigger. It looks like the radius only goes as big as 4 circles. So I'm going to do that. I'll put my chart over there. I'll make 4 concentric rings. And try to make it bigger so it's easier to see. Okay. I'm going to use green for my 30 and 60 degree lines. So 30, 60, 90, 120, 150, 180. And then I'm going to use red lines just so I can see where the 10 degree marks are. A little bit easier. So 10, 20, 40, 50, 70, 80. One 100, 110, 130, 140, 160, 170. All right. I got a lot of lines there. Let's see, can I use something that's, I'll use a Sharpie. So do I have a different colored Sharpie? I must. Yes. So at 0 degrees, I'm going to go out 4. At 10 degrees, it's 3.5. At 20 degrees, we're down to the second ring. At 30 degrees, we're at 0. At 40 degrees, I'm at -2. So there's 40 right there. So at 50 degrees, I'm at -3.5. At 60 degrees is the green line at -4. So it's doing this. At 70 degrees, I'm at -3.5. 80 degrees, I'm at -2. And at 90 degrees, I'm back to 0. At 100 degrees, I'm at 2. 110, I'm at 3.5. 120, I'm at 4. And then we start to come back inward. So yeah, I was at 150. At 160, I'm at -2. So we're following that line. We're over here. 170 is -3.5. And 180 is -4. I've started to connect. Let me see if doing another single point would help. What if I went 190 so that this is 570 degrees? This should be -0.866. It starts going back down, which means -3.5, 190 degrees. Right? 190 degrees is here. -3.5 is right there. So that's also 190 degrees also. You really don't want to stop until you've done several. It should at least connect back up completely. And oftentimes these make a pattern. And in fact, these shapes are called roses. So a rose, when we have r equals a sine n theta, it's going to have different results than r equals a cosine n theta. Let's take a look at these in DESMOS. Rather than doing these by hand, doing them by hand by one was enough. Torture is over. So here's a sine, it says b theta. Right now, b equals 2, a equals 2. What happens as a changes? As a changes, it changes the size. getting really small. It's going to get to 0. It'll go negative. See how it's making an X right now? Was it making an X earlier? Yeah, it was. So it's the same thing. N equals 2 led to 4 petals. B equals 1 is just 1 petal. Let's go up to 4. And anywhere in between, you get these really neat designs. So we'll let them run in a second. But we're looking at some mechanics here. I've got 1, 2, 3, 4, 5, 6, 7, 8. And negative 4 was no different than positive 4. Is negative 3 different than positive 3? That's negative 3. Yes. So on the odd petals, for sine, n equals the number of petals. When n equals odd, we have odd number of petals. And sine matters on n. When we look at n is even, we make it negative, it doesn't change the graph. When n is even, we have double the petals. But sine doesn't change the graph. So this was a little bit of an exploratory thing in DESMOS. Let's take a look at cosine. So right now we got B, let's make it positive. B equals 4, we've got 1, 2, 3, 4, 5, 6, 7, 8 petals. What happens when we drop down to 3? We're down to 3 petals. So it does the same thing. Does negative 3 matter? No, negative 3 did not change it, does it? Negative 5 versus positive 5, same graph. Let's look at 4 versus negative 4. Doesn't change it. Negative 3 versus 3. And again, A is just setting how big the flower gets. So for cosine, we have double the petals. If n is even, normal amount of petals if n is odd. And sine affects nothing. What happens if we put it in square root? It's kind of interesting, isn't it? The one with the regular graph is narrower. The one with the square root, the petals get wider. That's kind of interesting. What happens if we throw a square root or an absolute value sign in there? Now we're back to doubling it even if b is odd. You see that? So there's a lot of stuff going on with these things. In fact, I encourage you, let's do I have it up here? Let's take a look where we can find it in our course. Go to Files. I don't know how I have it up. Let's take a look and see if it will be in here though. Maybe PowerPoints will have it. Chapter 8.7. Let's see if they show the other graphs. Oh, that switches to the next document. It wants me to scroll down. Really? All right, back. There we go. Okay, let's just drag it down. So it shows things called limicons where it looks like a peach. It's got like a peach shape. But if the fraction dips below 1, it now starts going on the inside. It's called a limicon. The rose curves we were looking at, we looked at those. Circles are just by themselves. Lemniscates make this infinity symbol. And this looks at doing writing polar and rectangular and other forms. We took a look at it for a second and notice how bad it can get. Graphing these is tedious at best in polar. The spiral of Archimedes is really neat. R equals 2 theta is worth trying to graph. But you got to do a lot of these by hand. Practice doing 1 or 2, so you understand. I'm not testing you on this because let's face it, doing 1 graph by hand takes forever. And I know since we're going to be at home because we're in COVID-19 lockdown, I want to trust everyone, but I know how easy it's to say, oh, look, let me look at it at DESMOS. I know I'm going to be right the whole way. Then I'll just take my time with it. And it's just not worth it. You're not going to have to see this for a while. So it is worth knowing, seeing how it works. We will look at 8.8 tomorrow morning, and that'll be our last section. And I'll have a practice final up and a video on the final near the end of this week about how we're going to do it. And peace.